So this is Scott Manson. I'm from Schweitzer Engineering Laboratories. I spent the last 17 years at SEL working on various grid solutions, and including microgrids up to macrogrids for entire countries. The brief presentation I have today is to share the story of our participation in the NREL-sponsored Microgrid dual-stage procurement challenge. That's its technical name. We like to call it a Microgrid Shootout. It was an opportunity for us and all of our competitors around the world to put our best foot forward to NREL and provide a microgrid solution, both in terms of functionality as well as cybersecurity, and be evaluated by one of the nation's leading research laboratories. So this participation included a two-step. First step was a down selection from a number of candidates down to two. The second step of the procurement challenge was a down selection to a final selected control vendor, and that was SEL. This included a power hardware in the loop and a control hardware loop in the testing phase. The power hardware in the loop was stage 1, control hardware in the loop was stage 2. In addition, there was a cybersecurity evaluation by NREL during this functional testing to confirm or deny the proximity to standards such as NERC, SIPs, NIST, ISA, and others. We look for vulnerabilities most especially, and we performed flawlessly there. The key performance parameters we'll talk about in a moment, and Brian did mention them. This is the Banshee power system model. This is the same model used by MIT Lincoln Laboratories during their symposium in February of 2017. NREL took this model and added their control hardware in the loop simulation laboratory, here shown with the red box, the real generators, PVs, batteries. And here it is. They used their grid simulator as a source. They had a diesel generator in the yard. They had battery systems and photovoltaics with real inverters and real equipment. Our microcontroller's objective was to dispatch control those equipment in the yard simultaneous to all of the virtualized equipment on the control hardware in the loop model. Here shown is the interconnect. We had interconnects between our microgrid controller over a software-defined network. That's our SDN. And that interface included a multitude of communication protocols, including 61850, Modbus, and other. The test that was we were put up against for both the control hardware in the loop and the power hardware in the loop testing was similar to something perhaps you've heard of in North America, like a marine mud run. Anything and everything that can be thrown at you will be. The entire life of a microgrid was thrown at us in a 100-minute run. This was evaluated objectively by a MATLAB routine running in real time. The script was evaluating our performance on a number of key performance parameters. Here you see the actual mud run, the actual test sequence. We have irradiance changing. We have grid frequencies and voltages moving. We have demand response requests. We have faults on generators, interties, interconnects tripping out, motors tripping out. So a very difficult set of tests that make it impossible to be perfect. In fact, there had to be some decisions made. We'll talk about that in a minute. Here are the key performance parameters selected by Brian and his team. The most especially interesting one for me was resiliency and reliability. We ran a few tests and observed the response in terms of scoring, and realized very quickly that the resiliency was the way to achieve the highest score. So we focused on the technology which we had perfected in the oil and gas industry for nearly 20 years. But of course, additionally, we had to observe minimum fuel consumption, minimum emissions, of course, using as much of that low-cost photovoltaic energy as we could, and using battery storage as best we could. Here are some examples. Here's the real-time scoring for one of the runs for the KPP1. This is the resiliency and reliability parameter. What you'll see is that you have interruptible priority and critical loads. If we were to have tripped critical loads, we would have been docked a great deal of money. What we found, though, is that critical times when there was massive loss in generation or loss of the intertie is that a far better result was achieved by dipping into interruptible and priority loads with a very fast sub-cycle load shedding system. This stabilized the system instantly, prevented those inverters from tripping off, and then allowed us to reestablish a safe and normal operation of those microgrids. In fact, this microgrid, if you'll recollect to the first one line, broke into 3 microgrids, technically 4 if you chose to. Okay, so the next key performance parameter was fuel consumption. Of course, the objective here was to use as little fuel as possible. But we did use diesel. At times, it was necessary to use a lot of diesel to improve the reliability and to cover times when there was shading while you were islanded, et cetera, et cetera. Power quality was an interesting metric. This was about grid. This was a matter of voltage and frequency deviations from nominal. And what we would see is that during off-frequency events, part of our objective was to provide grid support. And so our controller, as it does in hundreds of field installations worldwide, provides grid stabilization support. And here was the typical final scoring. This was towards the end of our runs. You can see we ended with right around $3,000 US over a 100-minute run. The dark blue line is the final score, the totalized score. And you can see that we were, of course, using money on diesel, and we were gaining money by focusing on keeping the lights on for critical customers. Now, I'll show the same plot that Brian did, and I'll share some things here. So the first part of this, these are all the runs that we performed during the hardware in the loop testing. These shaded blue is the control hardware in the loop portion of the test. And what you'll see is that we achieved those $3,000 numbers towards the end of our runs. The second part was the control hardware in the loop testing. And then again, we achieved those same $3,000 runs. But what's interesting, as soon as we switched over to control hardware testing, we had new communication interfaces, new things to go wrong, and it was like commissioning a real power system. But it does point out that we achieved a significant improvement through control hardware in loop testing. But then again, another 10%, approximately 10–15% improvement. Improvement by performing power hardware testing. Now it does say that about 80 to 85% of the performance can be achieved with only control hardware testing. But what we have observed is you can get another 10 to 15, perhaps even 20% improvement by going through with a full power hardware test. And for new systems, I think new, innovative, different systems, we're advocating at SEL both PHIL and cHIL. Pardon me, I see a small error in the slide here. But where the 5,000 improvement was with power hardware testing. But what we, in all of our PowerMax projects worldwide, we have mandated for over 14 years that every project be tested in a control hardware in the loop environment. And this is the reason why. It's about quality, it's about delivering on time and on promise. So the products used to win both the cybersecurity and the microgrid challenge were the 3555 real-time automation controller. This is our quad-core, highest horsepower real-time engine. About a dozen PLCs capacity are in this single box. We had the PowerMax microgrid control libraries loaded onto that hardware platform. That's the most evolved PowerMax set of libraries. This was developed by myself and many others in the oil and gas and the DoD industries for maximum reliability of their power system. Okay, then finally the 2740S. This is a completely different approach to cybersecurity, and one that achieved us perfect scores at the NREL competition. So please look into those products, and I'll take any questions you might have. And Wallace, I'll take your lead.
Thank you very much for your presentation, Scott. It was really interesting.